Hello and welcome back. So we have already looked at the first three steps in setting up the FEM solution. We know how to formulate the equations, numerically integrate them, assemble the matrix, apply boundary conditions. So finally, we just have to solve, right? So we could do this simply in the slideshow format. I could just evaluate every expression step by step and just take the inverse like we did in FDM or FVM. But let's take a better approach. Let's do this systematically in an Excel sheet. So I have chosen an Excel sheet because number one, you can see all the changes happening in real time. So if you do this in a code, a lot of the change in numbers is happening behind the scenes. Okay, so in an Excel sheet you see everything in real time. So even if I were to change some numbers in the Excel sheet, so since all the data structure is really interlinked, so you see all the changes in real time, right? An Excel sheet is also accessible even if you are an experimentalist, biologist, chemist, so you will be using an Excel sheet. But at the same time, we also want this Excel sheet to have a good structure. So even if you want to go ahead towards coding, so this structure should be helpful. Okay, so I have kept that in mind while designing this Excel sheet. So please download this Excel sheet before you look ahead in this video. It will really help you. Open it in parallel while you see the video side by side. Try to play around with it. Okay, this is a hands-on approach and this will really help you. So let's look at now the problem that we are considering here. So this is a domain which is running from 0 to 1. So we are solving the Poisson equation here, minus del square u is equal to 10. Okay, we already looked at the analogy that we could extend this to a heat diffusion equation with a source, or a diffusion equation with a 0th order reaction. Okay, so the analogy is clear. So now let's solve this. So let's do this step by step. The first step would obviously be discretization. So we would have to discretize this geometry which runs from 0 to 1. So let's do that. Let's look at this part, which is the grid preparation. Okay, so in this part we are really discretizing first, right? So just divide into the set number of nodes, divide the geometry into the set number of nodes. Here I am taking 6 nodes, assign x coordinates to them. Here they are equispaced, but you could use different x coordinates as well. Then we generate these two kinds of informations. This is the element information. So this contains the information of which nodes are present in each element. So this helps to bring about the element connectivity. So I know that these two elements are connected because they have a common node. Okay, so when you start developing a code for unstructured grids, this is really important because you have to handle the node to node connectivity. So this is primarily important from a 2D case, but just as a good practice I have shown this here. Now also we look at the boundary info, right? So we have shown the nodes here, the boundary nodes, and we have also put in some flags here. So when you actually code, these are really helpful because instead of calling nodes, you can just call the flags. Okay, so because you could have multiple boundary conditions on multiple nodes. Okay, so just use one flag. Let's go to the next step, and that is the pre-computation step. So let's recall that we just do all the computations on the master element, right? And we also saw the numerical integration only takes place at the Gauss points. So we just store our polynomials at the Gauss points. Okay, so this is our master element running from 0 to 1. These are the Gauss points and Gauss weights. So let's just evaluate psi1, psi2 and their derivatives at these Gauss points. Okay, and we'll just pre-compute and store them, and that's what is done in most of the codes. And this really even helps you accelerate the codes because you have basically done the pre-allocations. Okay, the next step is writing down the test case. So this step is pretty simple. Mainly you just write down the boundary conditions, and you can just manipulate them as you want, right? So your Dirichlet boundary conditions, Neumann boundary conditions. In the PD we mainly have the source term, so we could change the source term to change the physics, right? So now let's go to the actual solution process. So this process is inside this table, right? In a code, you would have a for loop. Okay, so here we just write the first element and then we just drag it down. Okay, so here this is just some bookkeeping, this part. So we just write down the node, the x coordinates, we write the element and the node to node connectivity. We don't need the connectivity here, but just for a good practice I have written it down. The first computation is just compute this dx by dxi, the metric term or the j term. This is simply the element length, right? So we already know this, we have shown this. So now we'll come to these 6 highlighted elements, or these 6 highlighted cells, right? So these cells are really the crux of the entire Excel sheet. Okay, so if you understand these cells, you understand everything. So what we have done here is for every element we have calculated the K11, K12, K21, K22. So the local stiffness matrix entries, the local force vector entries. Okay, for this we have used the formulae which we have seen in the theory. So I am not going to go into these formulae again, and we just leverage these pre-computations here. Okay, so one suggestion that I want to do is just make a copy of this Excel sheet, delete all of these highlighted terms. Okay, and then rewrite them. Okay, rewrite them using these formulae which are provided here, or better just go to the slides, go to the theory, rewrite them and then just drag them down. Okay, and if this matches the solution, then you are basically good to go. You have already understood the heart of this entire process. Okay, let's go a bit ahead. Let's look at what's more in this Excel sheet. So here is the local stiffness matrix assembly. We have already seen this. So these are just the values which are copied from here. Okay, it's pretty simple. Then you assemble the global stiffness matrix. We have seen this again. So we can see that the node to node values get added. Same for the force vector, where you have a common node, you have an addition, right? So the key point to see here is the matrix, right? So you can see the matrix has 3 entries in a row and 3 entries in a column, right? So this kind of a matrix is called as a tri-diagonal matrix. Even in FDM and FEM you will see these kind of matrices. These are also called as sparse matrices, because even if instead of 6 nodes I would use 10 nodes, since the local approximation type is the same, you just have 3 entries. Okay, so this is a big matrix with lot of zeros. So you have special libraries for solving this in MATLAB or in any coding software in Python, right? So this is some thing about the matrix, and also you can see that this matrix is symmetric. Okay, so symmetric matrices are very easy to solve. Okay, so let's go ahead. So now we are applying the boundary conditions. We saw how to apply the Dirichlet boundary conditions which we are using here. Okay, then we calculate the inverse using the mean inverse formula, multiply it by the global force vector, and we get the solution. Okay, so here you can see the solution, and these parts are the errors, right? Because this is a linear solution, right? And this is your analytical solution. So now let's also quickly apply Neumann boundary condition. So here we saw that we just have to keep the stiffness matrix entries. So I have just copied the global stiffness matrix entry into the boundary condition application. Okay, I have overwritten the previous Dirichlet boundary condition. Okay, and I have kept the global force vector 0. So this is like du by dx is equal to 0, a flux equal to 0 condition. And you can see it here. It's pretty intuitive. Flux is equal to 0, so you have du by dx is equal to 0, right? No change in u. That's your boundary condition. You could also write this as, so let's look at the final row. So this row can be written as 5 into u6 minus u5 equal to 0. So that means u6 and u5 are just the same. So you are just seeing that here. Now if I were to put this as 1, okay, what would happen? Then I should get u6 minus u5 is equal to 0.2. Okay, so I'm getting this slope here. So now let's see if it is 0.2. So 6 minus 5.8, u6 minus u5 is equal to 0.2. Okay, so we are recovering that. Now we also saw if we had this kind of Robin boundary condition, du by dx is equal to 1 minus u. So we simply add this u6 here, right, in the unknowns. We add 1. So now this is your Robin boundary condition. So we have just had a quick look at how this solution works. Play around with this Excel sheet, have fun with it, and now we will, after this, so this is your Poisson's equation, which is very easy to solve using FEM. Now we'll look at the convection diffusion equation, and that we'll do in the next lecture. So here FEM will really struggle, and we'll have to do some upwinding to solve the problem. So we'll look at all of that in the next lecture. So thanks for your attention, and I'll see you again.